We'll talk about the problem first finding absolute maximum and absolute minimum of regular configuration. Then we apply this to a certain polarization problem. So we will. So let SD denote the unit sphere in the Euclidean space Rd+1, and let F be a continuous function defined on the closed interval 0, 4. So for a given configuration omega n of n points on SD, we define its potential in the following way. So we take F, the value of F, at a squared distance from x, from a given point x on the sphere to each point in the configuration, and we sum such values of the potential. And the purpose is to find the absolute maximum. The first problem is to find the absolute maximum of this potential over all points x on the sphere, as well as those points where this absolute maximum is attained. The problem of minimizing and maximizing the potential of some regular configurations on the sphere was considered before by Stolarski in his 2 papers in 1975 and by Nikolov and Rafailov later in 2011 and 2013. So they were considering the following potential functions. So when C equals 0, this is the classical Riesz potential, except I must put the minus sign. Here it is meant to be minus sign, just made the typo. And it's the Riesz potential. And that's when C equals 0. When C is greater than 0, this is a translation of the Riesz potential, which is a continuous function at 0. And so they considered such potential functions and configurations omega n of the following form. They considered n points, equally spaced points on S1, and found where minimum and maximum of that potential is attained. Also, regular simplex inscribed in SD, also regular cross polytope inscribed in SD, and Q. So what they showed for these configurations was the following. Again, there is the minus sign should be here, just missing minus. So for S greater than -2 and S not equal to 0, they showed that for all these 4 configurations, the absolute maximum of the potential is attained at the points of configuration itself. Of course, when C equals 0 and S is positive, this potential function is the classical Riesz potential. It is infinite at 0. In that case, the problem of maximizing is trivial. But if it's finite at 0, then it's not trivial problem. And the minimum is attained at the points of the dual configuration. So what do we mean by dual configuration? If you have n equally spaced points on the unit circle, then the dual configuration is this regular n-gon rotated by pi over n, right? So those are exactly the midpoints of the arcs joining the points of the configuration. That's a dual. For the regular simplex, it's just reflected about the origin. Reflect the simplex about the origin. Take minus omega. That will be the dual configuration. For the regular cross polytope, it is the dual cube. And for the cube, it is the dual cross polytope. So for S equals -2, the potential function appears to be constant. That's because these configurations are spherical designs, and that the fact that the potential is constant follows from that. And then when S is between -4 and -2, the situation switches. So now the minimum is attained at points of omega n, and the maximum is attained at the dual configuration. And then again, at S equals -4, the potential is constant again, because it's a design. And situation keeps switching. At every even negative value of S, the situation switches again and again, until we reach S equals -2m, where m is the strength of the configuration of the spherical design. So it switches after that one last time. And for all S less than -2m, it stays either this situation or the opposite situation. Stays all S less than -2m. That's what they showed. And in fact, what we observe is that this is controlled by the order of a certain derivative. The sign of a certain, not the order, the sign. The sign of derivative of a certain order of the potential function, of the Riesz potential function, it's either positive or negative. And depending on that, we have that maximum is attained at points of omega n and the minimum at the dual configuration, or vice versa. It depends on the sign of a derivative of a certain order. So we prove the following result. So let sigma sub d denote the d-dimensional area measure on SD normalized to be a probability measure. And let's recall the definition of a spherical design, which is due to Desart, Goethals, and Zeidel. We call the point configuration omega n a spherical n design if for every polynomial p on Rd plus 1 of degree at most n, the average value of this polynomial at the points of the configuration equals the average value of this polynomial of the whole sphere. And number n is called the strength of the spherical design. So following Kohn Kumar, recall that the point configuration omega n is called sharp. We add m sharp, we say m sharp to indicate the number of distances. If omega n is a spherical design to m minus 1 design, and there are n distinct values of the dot product between distinct points in omega n. And we also want to separate the case when sharp configuration is a design of order 2n. Okay, let us, for the purpose of the talk, call them strongly m sharp. So we'll say strong m sharp. That will mean that it's a sharp configuration, but design of order 2n. So examples of such configurations, there are several examples. First of all, odd number of equally spaced points on the unit circle, right? Odd number. So there are m distances, and it's a design of strength 2m, right? Even number of points is null, like that. Then regular siblings, another one example. Then there is a Schlafly configuration on S5 of 27 points. And there is another configuration of 275 points on S21. So there are such examples. We show the following. Suppose that f is a continuous potential function on 0, 4, differentiable inside of 0, 4, and the derivative of order 2n minus 1 is concave inside 0, 4. So if omega n is a strongly m-sharp configuration, then the potential of this configuration attains its absolute maximum over SD at every point of the configuration itself. And if the derivative of order 2n minus 1 is strictly concave, then those are the only points where absolute maximum is attained. So only at omega n, absolute maximum is attained only at omega n. So remember that this is such configurations that they are part of tight spherical. This is tight spherical design, one of the classes. And another class that we consider is sharp antipodal configurations. So just together with x, it contains minus x. So such are even number of equally spaced points on S1, vertices of regular cross polytope, regular icosahedron on S2, minimal vectors of E8 and each lattice for corresponding dimensions, and few more configurations, so you can find them in the table by Kohn and Kumar. So for this class of configurations, we have a similar theorem, except we assume that derivative of order 2m minus 2 of the function f is convex. We do that, and we do that omega n is antipodal m-sharp configuration. Then the potential of this configuration attains its absolute maximum again at every point of omega n. And if derivative is strictly convex of order 2m minus 2, derivative of order 2m minus 2 is strictly convex, in that case, no other points of absolute maximum exist. Well, this is another class of tight spherical designs. And I wanted to mention the sketch of the proof. We use the classical linear programming bound. You can find it in the paper of Kohn and Kumar, 2007. So first of all, when you have f of distance squared, right? Distance squared is the same as 2 minus 2 times dot product of x and y, right? So instead of f, I consider the function g, which is f of 2 minus 2t. This is a standard step. But now in the potential function, I have g of dot product x times xi, x dot xi. So first assume that omega n is strongly M sharp. And let T1 through T sub M be the values of the dot product between distinct vectors in omega n. We can show that -1 is never achieved if it's design over the 2M sharp configuration, design over the 2M. So there are both strict inequalities on both sides. And let P be the polynomial which interpolates value and derivative of the function, of the potential function G at every dot product. Plus, it also interpolates G at 1. So there are 2M plus 1 conditions. So this is a polynomial of degree at most 2M. And then, using the standard argument from interpolation theory, you can show that this polynomial stays above the potential function. Not below, it stays above because it interpolates at 1. So there is one more factor of T minus 1 in the remainder formula, which changes the inequality. So if omega n is a 2M design, because it is 2M design, you can show that this polynomial of degree at most 2M, this quantity is actually a constant function of Z. You can do this, for example, in the following way. You take this potential of evaluated polynomial, and because omega n is a design, the average value, this average value on the left equals the integral on the right. And of course, I multiply by instead of dividing. And then using the Funk-Hecke formula, this integral can be written as this integral, which is just a constant number. Then we take arbitrary point from omega n, denoted by y, and take arbitrary point x from the sphere. And we start with the value of the potential at x. And because P stays above G, the interpolating polynomial stays above G, we have this inequality. And then this potential is constant of the polynomial. So I can replace x with y because it's constant. And now y lies in the configuration and xi lies in the configuration. So y dot xi is one of the TIs, one of the dot products. And so there, P interpolates G. So again, I have equality. And then G, the sum with G can be written as the sum with F. So I have that at Y we have absolute maximum. So that's that. So the proof is pretty short. And when omega n is antipodal sharp configuration, the other theorem, then the proof is similar, except now one of the dot products is -1. One of the TIs, T1 is -1 because omega n is antipodal. Which means we don't have to interpolate derivatives there, just the function value at -1 we need to interpolate. So, which means we have, instead of 2M plus 1, 2M conditions. We interpolate at 1, at -1, and at M minus 1 dot products inside. So we have 2M conditions. So we need a polynomial of degree 2M minus 1, and omega n is a 2M minus 1 design, so the argument goes through. Notice that we did not need positive definiteness to show the maximum. We did not need. That would constitute most of the proof, right? The long proof. So here I would like also to mention that this technique of linear programming for minimal energy was also extensively used in the papers by Boyvalnikov, Dragnev, Hardin, Safin, Stoyanova, and also in the recent paper by Billy Glazerin, Matsky, Park, and Lesiuk. This is what concerns the problem of finding absolute maximum. So next we discuss the problem which we can solve using this result. Let's recall first the classical polarization problem. Well, let f be the potential function defined on the closed interval 0, 4, which allows now infinite value at 0. It is finite and completely monotone on the half-open interval 0, 4, modulo additive constant. So which means that f itself would become completely monotone after adding a constant. It's a sufficiently large positive constant. Like, for example, logarithmic potential would be like that, or Riesz potential with negative x. So now, given the configuration of omega n, again, we define its minimum, absolute minimum of the potential. Of its potential over the sphere, defined it by P sub f of omega n as d. And the classical polarization problem requires maximizing this minimum over all possible configurations of endpoints on the sphere for n fixed. And in those configurations, points can coincide, so there's no problem. Now we could consider multi-sets. So this is classical polarization problem. It has been considered extensively in mathematical literature. So the first works on polarization, on continuous version of the polarization problem, were by Otsuka in 1967 and by Stolarsky in 1975. Stolarsky considered the discrete polarization problem for just 3 points. And then later the works by Ambrose, Ball, and Erdely and Saf, Harding, Kendall, Saf, and other mathematicians. And also continuous version was considered in the papers, later in the papers by Farkas, Revas, and Nair. So in the continuous problem, instead of discrete set of points whose minimum of the potential you maximize, you have a measure, right? You have a Borel probability measure whose potential you are trying to, or for which you find the minimum of the potential, and then you maximize the minimum value. We'll deal in more detail here with known results on the sphere and unit circle. So for the unit circle, Stolarsky and then Nikolov and Rafailov showed optimality of equilateral points of the triangle for the risk potential and n equals c for 3 points. Then for s equals 2, an arbitrary number of points, Ambrose, Ball, and Erdely also showed the optimality of equally spaced points. Then for s equals 4, optimality of n equally spaced points was proved by Erdely and Saf. And then for any s greater than or equal to -1 by Harding, Kendall, and Saf, they showed the optimality of n equally spaced points on the unit circle. For the sphere, optimality is known for the regular simplex. Yuan Su in 2014 showed that 4 points on S2, the optimal configuration will be vertices of regular simplex. And then the presenter showed this for sphere SD for G greater than or equal to 0. Well, we can also consider the dual problem for this polarization problem. Instead of maximizing the minimum of the potential, we could minimize the absolute maximum. Of course, in this case, we have to assume that f potential function is finite everywhere. So recall our notation, we denoted by q sub f of omega n SD, the absolute maximum of the potential of the configuration omega n. And the problem 2 requires finding the absolute minimum of this quantity QF over all configurations of endpoints on SD. And finding configurations themselves that attain this minimum and is fixed. So there are here a few known results for optimality of these configurations on S1, Stolarsky, also 1 and 2. And we showed the following results. Suppose that D and M are greater than or equal to 1. F is a continuous function on the closed interval 0, 4, and a completely monotone on half open Z 0, 4 after possibly adding a constant. So I recall what does mean completely monotone. It means that on this interval function F is non-negative together with the function F is non-negative. Every even derivative is non-negative and every odd derivative is non-positive. That's completely monotone function. So suppose also that omega n bar is a strongly sharp or sharp antipodal endpoint configuration. Then the maximum of the potential of this omega n bar of this configuration does not exceed the maximum of the potential of any endpoint configuration on SD. So it is optimal. If F is strictly completely monotone, which means that inside the interval 0, 4, F together with its even derivatives is strictly positive and odd derivatives are strictly negative. f, at least f is such after possibly adding a constant. Adding a constant doesn't change the solution to this problem, but could become. So if f is strictly completely monotone after possibly adding a constant, omega n is such that equality holds in 2, equality holds here. So if omega n is optimal, then it has to be sharp, and the same dot products have to occur in omega n bar. And this result follows pretty easily from the known result of Kohn-Kumar for minimal energy or universal optimality of sharp configurations. Let me sketch the argument. So by assumption, derivative of order 2m minus 1 is concave on 0, 4, and derivative of order 2m minus 2 in convex. So because f is completely monotone, right? It means that derivative of order 2m is positive, which means derivative of order 2m minus 2 in convex. Derivative of order 2m plus 1 is negative, so derivative of order 2m minus 1 is concave. So, which means assumptions of both theorems on f that we stated for the maximum of the potential, they're satisfied. Omega n is strongly m sharp for some m. We apply the first theorem, and if it's sharp continual configuration, we apply the second theorem that we just mentioned. In both cases, the potential achieves its absolute maximum at points of omega n bar itself. Now let omega n be arbitrary configuration of SD. Then the result of Kohn-Kumar, because f is completely monotone and omega n bar is sharp, then we have this result for the energies. Well, the only remark must be made that we assume here that yi does not equal yj for different I and j. But because f is continuous, you can take the limit, use the limit transition, and still show this inequality, even when y1 through yn coincide in the generic configuration. We have this from the result of Kohn-Kumar, and then we start with absolute maximum of omega n bar. It is the maximum over all x of this potential. And now we use the fact that maximum is attained at a point of the configuration. Let that be xl, some point xl, or some l. But I can write this as an average of the energy, right? I can average it over all l with the same value, the same absolute maximum. So I can average, I can show that I see that this equals the average of such potential over all j's. So this is energy now. And I can delete from this sum xi and xj with the same indices. So if I equals j, I delete that from the sum. But because f is continuous at 0, there is no problem. I just add n times f of 0. And now I apply the result of Kohn-Kumar. So this is less than equal to then 1 over n times the energy of omega n plus n times f of 0. And I put it back. I put n times f of 0 back into the sum. That's when the case when I equals j goes back to the sum. And now this is the potential. This inside the sum is the potential of the configuration at yj. And the external sum is 1 over n, that's the average of the potential over n points. And the average over n points is less than or equal to the maximum. Average over n points is less than or equal to the max of the potential. And that's the quantity for omega n. We see that the quantity for omega n bar is less than or equal to the quantity for omega n. So that's how we prove this part. Then, this result immediately implies the following two corollaries. The first one is for the risk potential for s between -2 and 0. But we remove minus sign, which forces us to change minimum for maximum and change the direction of the inequality. So if s is between 0 and 2, and omega n bar is a strongly sharp or a sharp antipodal endpoint configuration on SD, then the following inequality holds. So the potential, the minimum of the potential of omega n bar is the largest possible. Exceeds greater than or equal to the potential of any configuration of endpoints. And if omega n is such that equality holds in 5, so if omega n is another optimal configuration, then it has to be sharp, and the same dot products have to occur in omega n and omega n1. Well, this result was proved for the equilateral triangle on the unit circle by Stolarsky. And we can prove a similar result for the Gaussian curve. If omega n bar again is a strongly sharp or sharp antipodal endpoint configuration and sigma is a positive number, then the Gaussian potential, the maximum of the Gaussian potential of a general configuration of omega n bar is less than or equal to than the maximum of the potential of the general configuration omega n. And again, the same uniqueness statement holds. And as the third part of the talk, we will discuss the problem of minimizing the potential over the unit sphere. So again, I mentioned that Stolarsky, Raphaelov, and Nikolov, they also found the absolute minimum of the potential for equally spaced points on the unit circle, regular simplex, cube, and cross-polygon. So they found the minimum as well. So here, when we talk about the problem of minimizing the potential, we allow infinite value for f at 0. Let f be a function defined on the interval 0, 4, which is finite and continuous on couple open interval 0, 4, and the value at 0 equals the limit of f at 0. Would be infinite. So given the configuration omega n on SD, we are required to find the absolute minimum of its potential over the sphere and points where this minimum is attained. So, and here we need some kind of analog of definition of sharpness, like another which would fit this particular problem. So we will consider configurations which are designs of order 2m-1 and which can be put in m parallel hyperplanes. So they are designs of order 2m-1, and there exists a point on the sphere which forms m distinct dot products with points of the whole configuration. That's the definition we have. Just for brevity, let's call them m stiff. Just another word to be different from sharp, tight. Just another word. Examples of such configurations are regular n-gon with n even number of points on the unit circle. Also, vertices of the cube. Cube is a 3 design, and you can put it into 2 parallel hyperplanes, the entire configuration. Regular cross-polytop as well. Interesting examples can be found for odd dimensions of the space, of the containing space on the sphere. And several examples can be found on S3, S5, and S6. And S3 is a 24/7, particularly. It satisfies this definition. We have the following result. So if f is a function which is continuous on the half open interval 0, 4, at 0 its value defines with the limit at 0, and differentiable inside the interval 0, 4, and derivative of order 2m-2 is convex, then, and omega n is such m-stiff configuration on the sphere, then the potential of this configuration attains its absolute minimum over SD at every point that forms m dot products with points of the configuration. So such points, let's call them dual configuration. So those points x, which form exactly m dot products with points of a given m-stiff configuration. So the minimum is attained at the points of the dual configuration. And if the derivative of order 2m-2 is strictly convex, then no other points of absolute minimum of the potential exist, only at the dual configuration. And the sketch of the proof is similar to the proof of the maximum. Again, I define g of t to be f of 2-2t, and my dot products t1 through tm, this should be t sub 1. Other values of the product, one can show that 1 and -1 are not among the dot products. These are not dot products. I made a typo here. These are not the values of dot products between distinct vectors in omega n. T1 through Tm are those m dot products that the point from the dual configuration forms with points of omega n. And they will be the same for every point from the dual configuration, and they are the zeros of the Gegenbauer polynomial. They will be zeros of the Gegenbauer polynomial because this is the proof goes through the quadrature formula with the highest algebraic degree of precision. So let P be the Hermite interpolating polynomial for the function G at these dot products. Then it has degree 2m-1 at most. And again, we can show that using standard argument that this Hermite interpolant will lie under the potential function G. That's because derivative of order 2m-2 is convex. And again, we show that the polynomial, this Hermite interpolating polynomial, has constant potential. And we can do it also using, instead of Fund-Hecker formula, like we did for the maximum, we can use its Gegenbauer expansion. So this is the Gegenbauer expansion of the Hermite interpolating polynomial. We still don't need positive definiteness of this polynomial. Because it is a design of strength 2m-1, we have these equalities. This is called moments. So the moments of order L from 1 to 2m-1, L is the degree of the corresponding Gegenbauer polynomial. So these moments are constantly zero on the sphere, exactly because this is a design of order 2m-1. And then because of that, the potential of this polynomial can be written through this Gegenbauer expansion, and these are zero moments. These are zero, so this is a constant value, a0 times n, just the first coefficient, the zeroth coefficient. Again, we show that it's constant, but that proof allows generalization. I'll talk about that later. And again, the same proof again. We start with arbitrary point on the sphere, which forms m distinct values of the dot product with points of omega n. So we start with any point y from the dual configuration and any x on the sphere. And the potential at any x on the sphere is greater than or equal to the potential for the interpolating polynomial, because interpolating polynomial lies below G. And then because this quantity is constant, the sum is constant, I can replace x with y. And these are dot products. Y dot xi, y is from the dual configuration, xi is from omega n. This is exactly T1 through Tn. This is the product. So P equals G there, it interpolates it, and that equals. So that's how we show that y is equal to V. And as you notice, not all sharp antipodal configurations are this stiff. For example, icosahedron is not. Because icosahedron, yes, it is a design of strength 5, but it is contained in 4 parallel planes rather than 3. And therefore, a modification of this technique is necessary. So in this Gegenbauer expansion, we need to include higher degree Gegenbauer polynomials, for which we still need this, the moment, the vanishing moment. And for icosahedron, for example, the moment of order 8 vanishes. So this vanishes for L from 1 to 5, and this also vanishes for every odd L because it's a symmetric configuration. But it also vanishes for L equals 8. So we need to take a polynomial of degree 8 now, where A6 would be 0, which would be orthogonal to P6, because the 6th moment doesn't vanish, but the 8th moment for icosahedron vanishes. We take such a polynomial, and there is still a way to show that it is less than or equal to than the potential function G. And the idea is used from the paper by Kohn and Kumar. They use this idea for 600 cell, and also Valenkov, Dragnev, Hardin, Stoyanov, and Saf used this idea extensively also for their works. So, and you can use this idea, this way of extending the proof, that's still showing that icosahedron find the minimum of the potential of the icosahedron. and some other configurations. This proof can be modified, extended to include some chart configurations which are not stable. Okay, so I'm finished.